let's revisit how Memo Choose works. So if you do Memo Choose 9.4, you end up with this table here, right? And this dimension is n, and this dimension is k, right? So what happens is that some entries will fill up as the memorization goes ahead, right? And some entries will remain false, or they will not be filled. Okay. Now, if you remember Pascal's triangle, it turns out that this whole table is filled in the same way as Pascal's triangle. Essentially, the two entries here will add up, and this will be the third entry. Okay, and you keep doing the same thing, and so forth. All right. So this way of filling out this table, you end up with this table. All right. So let's take a look at what this tells us. So the idea we come up with when we look at this table is the following. Why don't we just compute choose by filling up this table from the bottom, right? Because you know that the top is all ones, the sides are all ones, and you just add, 2 by 2, okay? And there's a name for this idea, and it's called dynamic programming. What's the order growth for this approach? Well, it turns out it's order n, right? But why? Well, if you look at the size of the table, what happens here is that once you fill up the table, we're done, and they are all together n by k entries, so it's kind of order n k. Right, let's take a look at how you would do choose. Okay, so we call this dp choose. Okay, the code is here. Let me just quickly explain this. Now, the first thing we do is that we allocate space for all the rows in the table. Okay, so here we create a whole bunch of ones. Right, this is a row of ones. Okay, and then we create empty table, which is a list. Okay, and then essentially we copy the row and we append the table. Right, so this creates a whole table of ones. A lot of ones, right? Okay, good. Now, it turns out that we know that the next one is that the first rows are all zeros. So we fill the first row of the table, right, with all zeros. Okay, and subsequently, the rest of the rows is filled by adding, remember, these two entries. You add together, you get the third entry down here, right? So basically, ij is I minus 1, j minus 1 plus table I minus 1, j. Right, so this is the sort of way you have to fill the table. And essentially, at the end of the whole thing, right, you return the entry nk. Okay, so this is the answer you return. Okay, let's take a look at how this will work. So in this particular piece of code, you will fill up the top row with all ones, okay, and then they're all together k plus 1 ones, right? And then after that, this set of code here will duplicate n plus 1 of those rows, okay, and this entry here is 0 0, right? This entry is k0, right? This is n0, and this is nk. Okay, now so what we do is that then we basically set the top row to all zeros like this. Okay, and next we are done with this row already, so this is also done. Okay, so now we will deal with the rest of the entries, right? And here what we do is that we basically set I to be this row, okay, j to be the column, right? And what we do is that we just add 2 together to form the third one, okay? And essentially we go down this way, right? And then once it's done, we change to 2 and so forth. Okay, then when we finish all this filling, we end up with 70, okay, which is the answer. So the next question is, can we adopt the same approach to solve the chocolate packing problem? Answer must be, of course, yes. Okay, how? So we take a look at the chocolate packing problem again. Okay, essentially, the key idea of dynamic programming is to fill up some kind of table, right? So the question here is, what does the table look like? So let's take a look. First is a table of list of chocolates versus a weight limit. Okay, and each table entry is the optimal choice for a given list and weight limit, right? So if you know chocolates, the answer is easy. It's empty set. There's no way to pack, right? The answer for a list of X types of chocolates is the better version of 2 possible answers. One is that you take the additional chocolate, okay, the new type, plus the optimal choice of remaining X minus 1 type, okay, or you basically have the optimal choice of just using the X minus 1 types of chocolates, okay. So this is similar to your count change, right? So let's take a look and see how we will build the table. Okay, so we have a table. The rows are the weight limit, and the columns are the types of chocolates that we have, right? So if there's no type of chocolates, it's nothing. Okay, there's no way you can do anything. Now suppose you have one type of chocolate A 4 2, okay, then essentially you fill up the whole row like this, right? Because over here, when your weight is less than 4, you can't do anything, whereas once the weight is 4, you have one chocolate, okay, and you have 8, you have 2 chocolates, okay. Okay, and essentially, as I mentioned, what happens here is that this particular choice here, over here, is the better of this one or this one plus A. So this one plus A is better, so this is A. Similarly, this is the better of this one plus A or this one. This one plus A is better, so A, right? Here is the better of this one plus A, which is AA, or this one, so it's AA. Okay, similarly, now we look at the next chocolate. So next chocolate, suppose is B and it's 5 3. So here you want to add B, but you can't add B because B is 5, here's only 4. So you check this thing. Now here you can add B, okay, from here, because now it's 5. You compare it to A. B is 3, A is 2, so B is better, okay. But then when you reach over here, right, you realize that 2 A's will be 4, 1 B will be 3, so 2 A's is better, okay. So you take this one, right, instead of the this thing plus B, right. Basically, you can go and write this in your spare time, okay, and you can pretty much do this post on the forum if you want to, okay. All right, let's look at one next example, and this example is of prime numbers. In recitation, we define a function called isPrime, which allows us to check whether a number is prime, right? Now, what happens if you want to check a whole bunch of numbers in interval from 0 to n and decide whether they're prime? Okay, so what you want to do is, given a number n, you want to return a list of true and false so that you tell whether or not the index is actually a prime or not, right? So let's take a look at isPrime again. All right, so this prime n. If n is 0, n is 1, then of course it's not a prime. If n is 2, it's a prime. Now, for n more than 2, what you do is that you try to divide n by the numbers from 2 to square root n, right? So if any of these numbers will divide n, then you know that n is not a prime, right? If everybody fails, then it's true, it's a prime. So this we know is order of square root n, order growth, right? So if you do it naively, okay, if you do isPrime n, and you do isPrime for I in range n plus 1. So this is list comprehension. So you go through everyone, and if you do your order of growth, you realize this is about order n to 3 over 2. All right, so we're going to do DP, and again, the idea is that we're going to compute the primes by filling out a table from the bottom. Right, so this is what DP prime looks like. First, we create a bitmap, right, that is true for all the elements in the range, right? Then we set 0 and 1 to false because 0 and 1 are not primes. Right, then we start from 2, okay. Now, if the bitmap I is true, then what we do is that we set all the multiples of I from 2I to n plus 1, right, with a step of I, right, to all false, and then we return bitmap, okay. So how does it work? All right, just take a look. So first of all, we start with all the numbers from 2 to 13, then we take 2, right, and then we delete away all multiples of 2, right, then that leaves 2 and 3, then the next one is 3, and we delete away all the multiples of 3, right, and then we go on to 5, okay, and they're all gone already, so nothing to do, and then we're left with 7, nothing left to do, and so forth, right. So then we do 11 and so forth. Okay, so this will work.